Okay, hi everybody. This is your next lesson. In this lesson, we're going to look at determining the type of chemical bond based on electronegativity. That's the focus. Okay. You'll need your periodic table for this lesson. If you look at your periodic table, here's carbon. Above the symbol and to the right of the symbol is a small number. That number is electronegativity for that element. Okay, so you want to refer to that number during this lesson. What is electronegativity? It's how strongly an atom is attracted to an electron that it's sharing in a chemical bond, as you can read there. Okay, so imagine when atoms are bound together, right, by electrons holding them together, how strongly each of the, imagine my hands are atoms here, how strongly each one is pulling on the electrons being shared. That's electronegativity. Okay. The value of electronegativity ranges from 0.7 to 4. So these little numbers here, lowest you'll see is 0.7 and the highest is 4. Noble gases do not have electronegativity values because they already have a full octet of electrons. They have a full valence energy level, and they usually don't bond for that reason. Okay. And what's going to happen, the difference in electronegativity between two atoms is what will determine if a bond is ionic or covalent. Okay. Oh, and these are your trends. So when you look at the periodic table, let's bring all that back up, come back. Okay, so when you look at the periodic table, as you go to the right and up, electronegativity increases, with noble gases being an exception. They don't have electronegativity. As you go down and to the left, electronegativity decreases. So the bond type. Difference in electronegativity, 0 to 0.2, is a nonpolar bond that's covalent. If the difference is 0.3 to 1.7, it's still a covalent bond, but that's a bond that we refer to as being polar, where one end of the bond is positive and the other is negative. And that's because the electrons are not shared equally. So the atom with the greater share of the electrons becomes negative because electrons are negative. And the atom that does not get electrons most of the time ends up being positive. Okay? With this first one, it's nonpolar, where there's pretty much no difference in electronegativity. All the atoms involved are sharing the electrons equally, so there's not much of a difference. Now, if the difference in electronegativity is greater than 1.7, that's an ionic bond, where the electrons are transferred rather than being shared in some way. Examples, Cl2, chlorine bonded with itself, is a nonpolar covalent bond. CO, carbon monoxide, is covalent, but it's polar. In this molecule, there we go. The carbon ends up being positive, and the oxygen ends up being negative, but it's still covalent. Now, sodium chloride, NaCl, table salt, ends up being an ionic bond. It's not even covalent. So what you're going to do now is you're going to fill in this table, fill it in the add puzzle. Okay? So looking at the first one, we have NO, a bond between nitrogen and oxygen. The electronegativity difference is 0.5. What type of bond is it? If you said polar covalent, you're correct. The difference is 0.5. That's in the polar covalent range. Oxygen with the higher electronegativity would have a greater share of electrons. It would be negative, and the nitrogen would be positive. The next one, magnesium and oxygen. The difference is 2.3. Choose your bond type. It is an ionic bond. Oxygen takes electrons from the magnesium. Bromide, what's called diatomic bromine, two bromine atoms, because it's the same element, there is zero difference in electronegativity. So what type of bond is it? It is a nonpolar covalent bond. Equal share of electrons. Next one, lithium hydride, lithium and hydrogen. Difference is 1.1. Choose your bond type. It is polar covalent. Good. Hydrogen has a greater share of the electrons. Lithium bromide, that's your difference. Choose your bond type. Ionic bond, very good. It's just over that line, so this wouldn't be ionic, where bromine takes electrons from the lithium. All right, what's next? Copper fluoride, 2.1 difference. Choose your bond type. Which one is it? It is an ionic bond. Fluorine takes electrons from copper. Next one, CO, difference of 1. Choose your bond type. It is a polar covalent bond. It's covalent, but it is polar. Oxygen has the greater share of the electrons. One last one, hydrogen and acetane, difference of 0.1. Choose your bond. That is a nonpolar covalent bond. And acetane has the greater share of the electrons. So in a nutshell, by looking at the difference in electronegativity, the second table here, you can compare it to the range that was provided in the previous slide, and that's going to tell you if the bond between the atoms is polar, nonpolar, covalent, or if it's ionic. Okay? And that's important because that'll give you information about how the molecule will interact with other substances. Okay, everybody, that's all for this video. I'll see you next time. So there's actually one more part to this lesson, and that has to do with polarity. Okay? What is polarity? Polarity is a situation in molecules where you have a difference in electronegativity, and the difference is significant enough that you get this sort of situation where in a bond, one atom becomes positive and the other one becomes negative. So water is polar. You probably know that. In water, here it is. Sorry, there we go. The oxygen has a negative charge and the hydrogens have a positive charge. And this molecule then behaves like a little magnet, okay? And it's attracted to other polar things. So that's polarity, and it happens in molecules, okay? So what is the deal with polarity? What we talk about with polarity in terms of attraction between molecules, like dissolves like is attracted to like, okay? So imagine if two different molecules, are they both nonpolar? They mix, okay? Like dissolves like mixes with like. Let's take a look. Here's a glass of water, and here's some sugar, okay? Just plain old table sugar, sucrose. Both of these molecules, water and sugar, are polar. So when I mix one into the other, they should mix. And sure enough, so sugar and water are both polar, they mix, okay? They're both polar molecules, and you end up with a homogeneous, a uniform mixture. Now imagine your molecules are both nonpolar. Are they both nonpolar? If so, then they mix, okay? Like dissolves like mixes with like, so nonpolar molecules should also mix together. Let's look at another example. So here I have some olive oil derived from olives and some corn oil derived from corn. These are both cooking oils, okay? Both nonpolar. So what I'm going to do is take some of the corn oil and mix it with the olive oil, and we'll see what happens. Here's our mixture. And again, just as before, we have a uniform, homogeneous mixture, no distinct layers there. The two oils mix because they're both nonpolar, okay? So nonpolar also mixes. Now, what if you have this situation, okay? What if one molecule is polar and the other is nonpolar? Hopefully by this point you can guess. There it is. They're not going to mix, okay? With polarity, opposite polarities do not mix together, okay? So let's look at one more example. We'll bring back the water. And even though it has sugar in it, it doesn't really matter. We'll just call it sugar water. And we have the corn oil. So I'm going to pour some of the water into the corn oil. Do you see what's happening? They're separating into separate layers. Let me try mixing them again. So even with some vigorous mixing, opposite polarities don't mix. Water's on the bottom, oil's on the top because it's less dense, and they don't mix. Nonpolar, polar. Opposite polarities don't mix, okay? So with polarity, you want to keep that in mind. Like dissolves like, okay? Polar molecules are like little magnets, like water, that are attracted to each other. Non-polar molecules are also attracted to each other. Opposite polarities don't mix. All right, thanks everybody, and I'll see you next time.